Transition probability for a constant perturbation. We have seen a complete video on this concept just before this video. And actually the aim of today's lecture is to find the transition probability when the perturbation is harmonic, or you can say periodic. In fact, we know this periodicity plays a very important role in nature, and there are so many fields which varies with time and position periodically. For example, if you talk about the electromagnetic field, you know in electromagnetic field, the electric and magnetic field vectors vary with time and position in periodic fashion, in harmonic manner. So if let us say a particle like electron will get interacted with an electromagnetic field, then the perturbation, that is the electric field, is since periodic or harmonic. So in that condition, the energy level of the electron will change, and how this energy level changes, what type of interaction will take place, that can be discussed on the basis of the time-dependent perturbation theory. And you know, the basic aim of time-dependent perturbation theory is to find the transition probability and its rate. So now we are going to discuss a very important problem today: how we can find the transition probability in case of a harmonic perturbation or periodic perturbation. Okay? For your examination purpose, particularly in M.Sc examination, such a question is independently asked. And if you want to write the answer of a question that discuss the find the transition probability for a harmonic perturbation, then some basic result which we have discussed in my previous videos, you must remember that, because starting from that result you can get the results of transition probability for a harmonic perturbation. So remember, when you have studied the basic theory of this time dependent perturbation, then we have obtained first of all a general result for the transition probability. But in that lecture I have told you that in most of the problems of atomic and nuclear physics, the first order transition probability calculation is sufficient, and therefore we are now only talking about the first order transition probability. And you have seen that this first order transition probability, which is denoted by the symbol PIF of t, that is defined like this. This is a square of the modulus of minus I over h bar times integral 0 to t times this quantity. This is actually the scalar product of v hat operated on kate psi with psi f, okay, and times e to the power I omega fit dt, okay. This expression we have seen in the first lecture on time dependent perturbation theory, okay. Here you know this v of t is actually the time dependent perturbation. Here we are going to discuss the harmonic perturbation. So definitely in this condition, this perturbation v of t will depend on time harmonically or periodically, okay. And you know the exponential function e to the power I omega t or e to the power minus I omega t is the best mathematical form, best way to express a harmonic function. So if you want to define this harmonic perturbation V of t, you may define it like this. This is a small v hat e to the power I omega t plus v hat dagger e to the power minus I omega t. In fact, here, this a small v hat, this is a time independent operator, not time dependent. E to the power I omega t actually introduces the time dependence of this v. Okay? And this v hat dagger, this is the Hermitian adjoint of this operator v hat. Okay? And times e to the power minus I omega t. Because any periodic vibration is expressed as in the form of e to the power plus minus iota omega t. Here omega is actually the cyclic or angular frequency of that periodic perturbation. Okay? If, for example, if you talk about the electromagnetic field, then this V will actually represent the electromagnetic field. Okay? And that this omega will then the frequency of the electromagnetic field. Okay? Now, considering this form of V, which actually implies that this capital V, which is perturbation term, this perturbation is harmonically varying perturbation, and if your aim is to find the transition probability PIF when the perturbation is harmonic, then what you will do? If your aim is to find only the first order transition probability, then in this general result, this V of t will be replaced by this much. Okay? So replacing that V of t by this much, we will have an expression for the transition, first order transition probability in case of periodic perturbation or harmonic perturbation. So let us see. Here, PIF of t. What I have explained earlier, everything is mentioned here. You can note down these things. Okay. This PIF of t will be what? This is a square of the modulus of minus I over h bar times integral 0 to t, this brass I. Now, at the place of perturbation capital V of t, I have written V, small v hat e to the power I omega t plus a small v hat dagger e to the power minus I omega t. This is at the place of this perturbation V of t. Okay? And this much. Now see, as a square of the modulus of minus I, that will be 1. So this is 1 over h bar square. And it is a constant factor, so this is outside of the integral. Again, you can see this psi f, that is brass psi f, will be operated on this v hat e to the power I omega t and v hat dagger e to the power minus I omega t, and also this kate psi will be operated. So operating this, first of all let us see, this will be the scalar product of this v hat psi I with psi f, okay, times integral 0 to t. Now see, when this e to the power I omega t here, okay, and e to the power I omega fit in outside, both will be multiplied, okay, and so that will become e to the power iota times omega fi plus omega times t and dt. Now similarly, now we will take the product of this brass psi with v dagger and this kate psi, okay, and again this e to the power minus I omega t will be in the integral part. So this can be written as this quantity times integral 0 to t e to the power I omega fi minus omega. Mark it. Here there is minus omega t dt. Okay. In fact, in this for when we have written this expression, okay, then actually the cross term has been neglected. When you say if you evaluate the square of modulus of this much, you know this a plus b whole square, a plus b whole square. What will be this? This is a square plus b square plus 2ab. Actually here this 2ab term is called cross term because here a and b are multiplied and both are different. So this is called cross term. Now let us consider that if this cross term 2ab is much smaller than a square and b square, then we can neglect this 2ab. But this can be neglected only when this cross term will be negligibly small in comparison to the remaining terms. Actually here in this case it is found that the cross term will be negligibly small. So when you will find the square of the modulus of this quantity, okay, then you have to take the square of the modulus of individual quantity, that is only a square plus b square, and we will neglect the cross term. So that result can be written like this: PIF of t equal to 1 over h bar square, this much square times. Now let us see. The integral of e to the power I omega fi plus omega times t will be what? And after integrating, you will have to square it. Okay. So let us see. The integral of that function is e to the power I omega fi plus omega times t and divided by omega fi plus omega. I times omega fi plus omega. Okay. And when you will square, then 1 over I square, this is equal to 1. Okay. And when you will put the limit, after putting the limit t, the first term will be e to the power I omega fi plus omega into t divided by this much. And in second term, there will be e to the power 0, which is 1. So I have directly written it here. You can check it. Okay. Now, let us take the square of the modulus of second term. This will be again 1 by h bar square, square of modulus of this quantity, and times square of the modulus of e to the power I omega fi minus omega times t minus 1 over omega fi minus omega. Actually, this has been written at the place of integral of this much. Okay. So this expression we have obtained by neglecting the cross terms, because I have told you that the cross terms are actually negligible compared with the other two. And why that is negligible? Because they induce no lasting transition, and therefore we can neglect the cross term. Okay. Now, in this result, when we will use this formula, e to the power I theta minus 1 mod square. Actually, in my previous lecture, I have written this formula, and so you can remember that a square of the modulus of e to the power I theta minus 1, this is simply equal to 4 sine square theta by 2. Okay. So we can simplify this result: e to the power I omega fi plus omega times t minus 1 mod square. Okay. Instead of it, you can write what? 4 sine square omega Fi plus omega into t divided by 2. You can write. And again, instead of the square of the modulus of this e to the power I f omega Fi minus omega into t. Here at the place of theta there is omega Fi minus omega into t. So this will be again 4 sine square omega Fi minus omega into t divided by 2. So in fact 4 over h bar square I have taken as a common factor. Okay. And when you will take this 4 by h bar square as a common factor, then the remaining terms will be a square of the modulus of this quantity times sine square omega Fi plus omega times t divided by 2 and divided by omega Fi plus omega whole square and plus a square of the modulus of this quantity, okay, you can see, and times sine square omega Fi minus omega times t over 2 and divided by omega Fi minus omega whole square. Okay. So this is the expression for the transition probability in case of a harmonic perturbation, or you can say a periodically varying perturbation. Okay. Now when we have discussed the transition probability for the constant perturbation in our previous lecture, then you have seen that this factor sine square omega Fi plus omega times t divided by 2 and divided by this much. Actually, the property of this function just resembles with the property of Dirac delta function in the limiting condition when t tends to infinity. Okay. So in the limiting case, t tending towards infinity, the behavior of this sine square function actually is just appears like a delta function. Okay. And so you can see if then if you will plot, first of all let us see, if you will plot this pif of t in against of omega Fi, which is actually the transition probability, you know, this is Ef minus Ei divided by h bar. Then as you can see in this figure, the transition probability peaks at omega Fi equal to minus omega. See here, this is the first peak, max. Here the transition probability is maximum. Actually, this figure shows the graphical plot of sine square omega Fi plus omega times t divided by 2 and divided by this much, and also of sine square omega Fi minus omega into t divided by 2 divided by this much. But you know, this is the factor of the terms which define the equation pif of t, and except this other factors are constant. So the variation of pif t will with omega Fi will be just determined by the variation of this function or this factor. So in the graph I have not written here, you can write here pif of t, the graphical plot of pif of t in against of omega Fi or this much. Okay. And as we see in this figure that when omega Fi, see here, here is origin and the value of omega Fi has been written here, this is omega Fi on this axis. Okay. So the values of omega Fi written in left side of O will be taken negative and that in right side are taken positive. And from the figure it is obvious that when omega Fi is equal to minus omega, there is a transition probability peak. It means the transition probability is maximum. This is called actually the central maximum or the main maximum, you can say. Okay. And what will be actually the maximum value of this transition probability when omega Fi is equal to minus omega. Okay. So PIF of t in this condition will be what? In fact, in the general expression for this term, okay, when for this term, when omega will be actually equal to, omega Fi will be equal to minus omega, then when you will put this condition in here, omega Fi equal to minus omega, okay, minus omega, then the expression for PIF t will be maximum, and this maximum value after substituting omega Fi barabar minus omega in that expression, you will get t square over 4h bar square times a square of the modulus of the quantity this much. This is the maximum value, okay, and it occurs when omega Fi is equal to minus omega, where omega, you know, this is the frequency of the external field, that is the external perturbation. And you can also see the transition probability again peaks when omega Fi is equal to omega, okay. And if you want to find the maximum value of this PIF of t in this condition corresponding to omega Fi equal to omega, then what will be this? This will be again t square over 4h bar square, a square of the modulus of the quantity psi f v hat dagger psi I mod square. Okay, this is its maximum value. In fact, you can see that this transition probability is maximum, or it has central maximum when omega Fi is equal to minus omega or plus omega. What is this omega? Omega is the frequency of the external field or frequency of the perturbing potential. And omega Fi, this is the transition frequency of transition from state I to F. So when the frequency of our system becomes equal to the frequency of the source, that is the perturbing potential, then we have transition probability peaks. This is actually the conditions of resonance. You have definitely studied resonance in your course on electricity and also in your course on waves and oscillation. And you know, when the frequency of an oscillator or its natural frequency matches, resembles with the frequency of the applied force or the external source, then resonance takes place. Amplitude of the vibration becomes maximum. Here, transition probability is maximum. But when omega Fi is equal to either plus omega or minus omega, or you can say when omega is equal to plus minus omega Fi. So this is nothing, this is simply the conditions for resonance. So you can say that the probability of transition is greatest only when the frequency of the perturbing field is close to plus minus omega Fi. Not exactly equal, it may happen that when omega is almost equal to plus minus omega Fi, then resonance will take place. We will have the max highest or the peak value of the transition probability. And you can also see from this figure, as one deviates from this value of omega or minus omega, the value of the transition probability rapidly falls. It rapidly decreases. So you can say as omega moves away from this plus minus omega Fi, then Pfi or Pif decreases rapidly. Okay? So I think what has been depicted in this figure, you have clearly understand. All those facts I have mentioned it here, you can see. I have shown in the adjacent figure that transition probability peaks either at omega Fi equal to minus omega or at omega Fi equal to plus omega. You have seen. And what is the maximum value of Pif of t? This is t square over 4 h bar square times a square of the modulus of this quantity. And again, the maximum value of transition probability when omega Fi is equal to omega. This is the maximum value when omega Fi equal to minus omega. In that condition, Pift has a maximum value given by this relation. Sometime later in this video, you will see that actually this quantity which I am marking here and this quantity are actually same, because the operator V hat is a Hermitian operator. So in that condition you will see that both of these quantity will be equal. So in fact the transition peak is same when omega Fi is either minus omega or it is equal to plus omega. Okay. So these are the conditions of resonance as I have told you. This means the probability of transition is greatest only when the frequency of perturbing field is close to plus minus omega Fi. And as omega moves away from plus minus omega Fi, Pif decreases rapidly. Okay? And therefore, as I have told you, that the behavior of this Pif of t is just like a delta function in the limit t tends to infinity. Actually, this idea I have discussed in very detail in the first video on this time-dependent perturbation theory. So I have not given here the detailed analysis because you have already learned that as you can see at omega equal to plus minus omega Fi, this Pif of t is maximum, but as the value of omega deviates from that value plus minus omega Fi, then rapidly Pif of t decreases. This is actually the behavior of delta function. So I have written here that the behavior of this Pif of t is just like delta function, but not always in the longer time limit. When t tends to 0, then this function will just behave like a Dirac delta function. And so you have learned in the previous lecture that in that condition, this expression sine square of omega Fi plus minus omega times t divided by 2 times 1 over 1 by 2 omega Fi plus minus omega whole square, that is equal to this much. I have written it here directly. If you want to know the explanation of this expression, please watch the first video on perturbation theory where I have discussed it in more detail. Okay? But you know, that this H bar omega Fi is equal to EF minus EA. All these things we have learned earlier. Because you know this transition frequency omega Fi, this is simply EF minus EI divided by H bar. So what is H bar times omega Fi? That is EF minus EA. So I have written it here, H bar omega Fi is EF minus EA. Okay? And therefore, in this expression, see here, you can write PIF of t equal to 2 pi t over H bar times a square of the modulus of this quantity, okay, and delta of EF minus EI plus H bar omega. Here, see, I have written here plus minus sign both for the result, but here for plus omega and minus omega term will be different. And plus 2 pi t over H bar, a square of the modulus of this quantity times delta function of EF minus EI minus H bar omega. Okay? So this is actually the first order transition probability in case of the harmonic perturbation. Okay? Now, after getting the result for this transition probability, now we can define the rate of transition probability, or you simply say transition rate. And what will be that transition rate? You know, transition rate means transition probability per unit time. Transition probability per unit time, that is called transition rate, and it is denoted by the symbol gamma IF. So gamma IF, this is equal to PIF of t over t. And therefore, from this very equation number 5, you can easily find the transition rate. When you will divide this PIF of t by t, the t present in RHS in both terms will cancel out, and therefore this gamma IF is equal to 2 pi over H bar times a square of the modulus of this quantity times delta of EF minus EI plus H bar omega, and plus 2 pi over H bar times a square of the modulus of this quantity. In fact, here there will be dagger, okay, V dagger, and this much. Now see here, you know the property of delta function. If you denote the delta function by the symbol delta x minus x naught, you know this is infinity for x equal to x naught, and this is 0 for x not equal to x naught. This is the basic definition of delta function. So here you can say that delta EF minus EI plus H bar omega, this is not 0, but it will be infinity. But when EF is equal to EI minus H bar omega, EF is equal to EI minus H bar omega. It means EF minus EI, that is equal to minus H bar omega. Okay, in not equal to H bar. So in that condition, delta function is not 0. Okay. Again, if EF is equal to EI plus H bar omega, then again this delta function will be not 0, but it will be infinity. So this result implies that the transition rate gamma IF, this is not equal to 0 when EF is equal to EI minus H bar omega, or EF is equal to EI plus H bar omega. When these two conditions will get satisfied, then transition rate will be not zero. It means transition will take place. Our system will move from one stationary state to another stationary state after the interaction with the periodic potential, or you can say periodic perturbation or periodic field. Okay? But when EF is not equal to EI minus H bar omega, or EF is not equal to EI plus H bar omega, then it will be zero. Then actually there will be no transition. But you can see, can these two conditions will get satisfied simultaneously? Answer is no. Both of these conditions cannot be satisfied simultaneously. Okay? Then how we can understand the physical meaning of this equation? So now let us try to find what these equations actually physically refer. Okay? So actually, to know the physical meaning of these equations, you can see that the first condition, which we have written EF equal to EI minus H bar omega. What actually this equation implies? See here this diagram. EF minus EI. Here, EI is the initial state of our system. Okay? And the energy of the system in initial state, EI, is greater than EF. Greater than EF. So, in this condition, this initial state is actually the excited state of our system. Okay? And this is the state of lower energy, or if it is the state of lowest energy, then you may call it ground state. But it may not be a ground state. This may be an excited state, but of lower order. So in this condition, you can say that this equation EF barabar EI minus H bar omega, this actually implies that our system was initially in an excited state, and since its final energy is smaller, EF is smaller, okay, than the initial energy, so when acted upon by the perturbation, the system de-excites, and during this de-excitation, this system actually emits a photon of energy H bar omega, which will be equal to EI minus EF. So in this condition, after the interaction of the system with the perturbing potential, the system transits from its initial state to its final state, emitting a photon. Okay? So this process is actually called a stimulated emission. Why the word stimulated? Because the transition of system from the initial state, that is from the excited state to the lower energy state, does not take place automatically, does not take place spontaneously, but it happens. The system transits from the excited state to the lower energy state only when it is interacted with the harmonic perturbation. After that, this emission of photon takes place. So it is called a stimulated emission. It means the perturbing potential or the perturbing field actually stimulates our system in its initial state to move to the lower energy state. That's why it is called a stimulated emission. In fact, you know, this stimulated emission plays a very important role in case of laser production. And this was Einstein actually, which first of all talked about this stimulated emission. Before Einstein's idea, there was no concept of stimulated emission. People think that if a system is in an excited state, in a state of higher energy, it will spontaneously emit the energy and move to the state of lower energy. But there are some excited state from which our system does not move to the lower energy state spontaneously, but it moves only when there will be an stimulating field or inducing field, that inducing field which compel the system to move from excited state to lower energy state, that is actually the perturbing field. Okay, and that actually happens in case of the laser production, and this very phenomena is called stimulated emission. Okay, now what is the meaning of this equation when you say EF equal to EI plus H bar omega? So here actually our system is initially in the lower energy state. This is lower energy state, low energy, and this is high energy, HE, or you can say this is excited state. So in this condition, what actually happens? In this condition, our system absorbs a photon of energy H bar omega, whose energy is exactly equal to the difference of the energy of this higher energy level and this lower energy level. So if a photon has energy just equal to EF minus EI, then that photon will get absorbed by our system in the lower energy state, and gaining this much energy H bar omega, the system transits to the higher energy state or the excited state EF. So in this case there is an absorption of a photon, and that's why it is called absorption. This phenomenon is called absorption. Actually, there is no need to say stimulated absorption, because absorption is always stimulated. Okay, it will never happen that our system will move from the lower energy state to the higher energy state spontaneously. Never it will take place. It will take place only at the cost of absorption of energy from outside. So absorption is always stimulated. So stimulated emission, stimulated absorption term is not used. We simply say absorption. So I have written here, you can see that EF equal to EI plus H bar omega shows that the final energy of the system is larger than its initial energy. Okay, and the system then absorbs a photon of energy H bar omega from this perturbing potential V of t or perturbing field V of t, and ends up in an excited state of higher energy EF. Okay, this process is called absorption. Okay, thus the terms e to the power I omega t and e to the power minus I omega t in V of t as responsible respectively for the emission and absorption. In fact, this term e to the power I omega t present in the expression for this V hat, capital V hat. We have seen this is V, small v hat, e to the power I omega t plus small v hat bigger e to the power minus I omega t. In fact, this e to the power I omega t term, this is responsible for the emission, that emission of photon or emission of radiation, and e to the power minus I omega t, this is responsible for absorption. This is responsible for absorption. Okay. So I think now the idea of transition probability calculation for harmonic perturbation or periodic potential you have clearly understand. Now let us see, you can say as a conclusion that the effect of harmonic perturbation is to transfer to the system or to receive from it effect of harmonic perturbation is to transfer to the, in fact, is to transfer to the system or receive from the system or receive from it a photon of energy h bar omega. So whenever you will talk about harmonic perturbation, what will happen? Either there will be an absorption of a photon or an emission of photon. So you can say that in this condition, either our system absorbs energy or rejects energy or ejects energy or loses energy. So energy does not remain conserved. The energy of the system does not remain conserved. This is actually completely in contrast what we have learnt in case of constant perturbation. You have seen that in case of constant perturbation, the energy of our system was actually same in the initial and final state. In that condition, you have seen that EI is equal to EF. When EI is equal to EF, when you talk about the constant perturbation concept. But in case of harmonic perturbation, either our system absorbs energy which is equal to h bar omega, or it emits energy which is equal to h bar omega. So in this case, you can say that there is a net transfer of energy either from the system to the perturbing potential or from the perturbing field to the system. There will be an exchange of energy between the perturbing field and our system. Okay. Now, regarding this transition probability calculation for harmonic perturbation, now let us see a very remarkable fact. Okay. In fact, while talking about the transition probability for constant perturbation, I have talked about a very famous rule which is called Fermi golden rule. Remember, you have watched in the previous video this Fermi golden rule. And what is this Fermi golden rule? Actually, this Fermi golden rule is nothing. This is simply the transition into a continuum of final states. When you talk about the final state, that is kth psi f, or the state of energy EF, is continuous. In that condition, when you find the total transition rate, that total transition rate is actually then called Fermi golden rule. And you have seen in case of the constant perturbation, this total rate of transition WIF is given by this result, 2 pi over h bar, a square of the modulus of this quantity times rho of EI. What is this rho of EI? Rho is called density of states. And when you say density of a state, that means the number of quantum state in unit energy range. And this result I have written directly because I have already derived this result in my previous lecture. Okay. Now, with an analogy of this result for the total transition probability in case of continuum of final states, you can write the expression for the total transition rate in case separately in case of absorption of energy and emission of energy. Because in case of harmonic perturbation, the system either absorbs energy when it is in ground state and move to some excited state, or it emits energy in the form of photon when initially the system is in its excited state and moves to the ground state. So, on the basis of this result or with an analogy of this result, we can easily write, not find, the expression for the total transition rate separately for the case of absorption of energy and case of emission of energy. So let us see. WIF, and in superscript I have written ABS. That ABS actually stands for absorption. That will be given by 2 pi over h bar and the square of the modulus of this quantity. You can see here there is V dagger because this operator V dagger is responsible for absorption. You have seen. Okay? And times rho of EF. And here EF is equal to EI plus H bar omega. You have seen earlier. And again we know this WIF EMI I have written, and EMI that is for emission, okay, and that will be written like this, okay. But as I have told you earlier that when you talk about the periodic perturbation V of t defined like this, okay, in the actually this perturbation or this operator V hat is a Hermitian operator, and you have studied earlier in my previous videos in very detail the properties of Hermitian operator. And you know, if this V hat of t is a Hermitian operator, then this quantity will be equal to this much. It means when you will actually interchange the Bryant-Kate vector and take its complex conjugate, here a star means complex conjugate, then both will be equal. And therefore, you can write that the square of the modulus of this quantity is equal to a square of the modulus of this quantity, which I have told you earlier. So in fact, in this expression, both of these quantities are equal, and therefore if you will find the ratio of the total rate, transition rate, WIF ABS and WIF emission, then this will be equal to this much. Okay. Actually, this relation is known as condition for detailed balancing. Okay. So I think now after discussing this transition probability for a harmonic perturbation, the basic concept of time dependent perturbation theory is very clear to you. Okay. Thank you very much.